Hi, I'm Harry, and welcome to the long-awaited third session of MindSpore TechDay. And hello, Sophia. It's been more than a year since we had a talk about AI frameworks. How have you been?
Hi, Harry. I've been good. Can't believe it's been that long. What have you been up to?
Well, I've been diving deep into AI. I've been learning to use the MindSpore AI framework. It's been a challenging but rewarding journey. I've built some cool projects with it.
That's awesome, Harry. MindSpore is no joke. What kind of projects have you been working on?
I've been working on image recognition and natural language processing tasks. It's fascinating how AI can do so much these days. I even developed an image-to-image translation prototype using MindSpore.
That sounds really interesting. As for me, I've been exploring the world of OCR, optical character recognition. I tried my hand at training a model to recognize Chinese and English characters in scanned documents. It's been quite a challenge, but I've made some progress.
OCR, it's a valuable skill, especially with the increasing digitization of documents. How's this going?
It's been a learning curve for sure. Training the model to accurately recognize characters in both languages has been a bit tricky, but I'm getting there. I'm hoping to refine it and maybe even turn it into a useful tool someday.
Keep at it, Sophia. That's some impressive work. We should definitely collaborate on something AI-related soon.
Absolutely, Harry. It's great to catch up and share our AI adventures. Let's definitely brainstorm some cool projects together.
Speaking of AI, I've been really impressed with how versatile the MindSpore framework is. It's designed to be flexible and easy to use, which makes it perfect for both beginners and experts.
That sounds promising. Can you give me a brief overview of the design philosophy behind MindSpore?
Sure thing. MindSpore follows a unique hybrid approach, combining the best of static and dynamic computation graphs. It allows you to define a network once and execute it dynamically, which is excellent for debugging and development.
That does sound flexible. How about distributed training? I've heard that's a crucial aspect of modern AI frameworks.
Absolutely, Sophia. MindSpore has strong support for distributed training, making it suitable for large-scale projects. It uses a concept called parallel mode, which simplifies the process of scaling your model across multiple devices and GPUs.
That's impressive, Harry. And what about model deployment? That's always a challenge in AI deployment.
Well, MindSpore has got you covered there too. It provides tools for model conversion and deployment across different platforms, including mobile devices and edge devices. It is designed to be versatile and adaptable to various development scenarios.
It sounds like MindSpore has a well-thought-out design. I'm definitely interested in exploring it further.
The exploration of MindSpore is exactly what we're going to cover today. Speaking of AI frameworks, they've been shaped by 4 key factors over the past decade. Do you happen to know what these factors are?
I'm aware of 2 of them. Developer experience is definitely one. An AI framework needs to strike a balance between algorithm development efficiency and operational performance. Another factor is compatible with our algorithm and data, as an AI framework needs to handle increasingly large models and the new computing workloads. However, I'm not sure about the other 2 factors.
You've nailed the first 2 factors. Now let me shed some light on the remaining 2. Hardware enablement is another crucial aspect to consider. You want an AI framework to harness the full potential of available hardware resources, such as chips and clusters. Last but certainly not least, there's deployment capability. In today's diverse landscape, AI is employed across various industries, scenarios, and devices. Ideally, an AI framework should be deployable on a wide range of devices, be they servers, PCs, or mobile phones. This versatility is key to its success.
So, how does MindSpore measure up when it comes to these four factors?
MindSpore has been meticulously crafted to excel in a wide range of scenarios, including device, edge, and cloud. Its primary goal is to bridge the gap between AI algorithm research and practical deployment. Here, I'd like to show you the overall architecture of MindSpore. In the early stages of algorithm development, MindSpore offers developers a unified programming experience to streamline and enhance the efficiency of their work. As you move into production, it employs automatic parallelism to significantly boost development and debugging efficiency in distributed training while making optimal use of diverse hardware resources. And when it comes to deployment, MindSpore's unified architecture addresses the challenges of enterprise-level deployment and ensures robust security and trustworthy. It's a versatile framework designed to shine at every stage of the AI journey.
Its capabilities sound promising, but I still have some concerns. When I work on AI models, I've noticed that traditional object-oriented programming, OOP, doesn't always align perfectly with a typical workflow and paradigms in machine learning. While OOP can represent structures like tensors and metrics, it often falls short in terms of efficiency. Moreover, OOP's emphasis on abstraction and encapsulation can introduce unwanted overhead, impacting code performance and making optimization a challenge. At times, I find myself turning to functional programming to ensure immutability and work seamlessly with the declarative and mathematical nature of algorithms. Can MindSpore help me address these issues?
Absolutely. MindSpore takes into account the need for flexibility and ease of use in neural network model construction and training. It combines MindSpore's own functional automatic differentiation mechanism with a functional and object-oriented fusion programming paradigm for AI model training. This approach allows you to harness the strengths of both paradigms. Additionally, the same automatic differentiation mechanism is used to ensure compatibility between deep learning backpropagation and the automatic differentiation of scientific computing, providing a solid foundation for AI and scientific computing modeling.
Let me process that. So, with this fusion paradigm, I can construct neural networks using classes, create instances of neural network objects, define forward functions, and then derive back propagation functions through function transformations.
Precisely, with these techniques at your disposal, you can easily build your training process function and initiate the training process with greater ease and efficiency.
That sounds fantastic. Training becomes much more manageable with this approach. Another challenge I've encountered in model training is the choice between static and dynamic graphs. As you are aware, traditional AI frameworks typically rely on either static or dynamic graphs to construct and represent computational graphs. Each approach has its own set of advantages and disadvantages. I'm curious to know if MindSpore offers a way to combine these approaches, allowing for more flexible utilization of their strengths.
You've hit upon a crucial consideration in AI framework selection. In general, static graphs tend to deliver higher performance but can be more complex to work with, whereas dynamic graphs offer greater flexibility and ease of use, albeit at the expense of some performance. MindSpore addresses this by offering both static and dynamic graph modes through the setContext API. You can switch between these modes by setting it to MS Graph mode for static or MS PyNative mode for dynamic.
I'm familiar with the option to choose modes during coding, but my concern is how to efficiently use both modes together. I understand that in static graph mode, Python code isn't executed by the Python interpreter. It's compiled into a static computational graph. However, due to restrictions in syntax parsing, not all Python data types, syntax, and operations are supported when building a static graph. How does MindSpore tackle this challenge?
That's an excellent question. MindSpore takes inspiration from traditional just-in-time compilation or JIT compilation and extends the syntax capabilities of the static graph mode to achieve a seamless integration of static and dynamic graphs.
So does this mean I can run Python code without restrictions when using the static graph mode?
Not precisely. MindSpore achieves the unification of dynamic and static graphs by supporting static compilation within the dynamic graph mode. If you have a function that you want to execute in the static graph, you can simply add a JIT decorator to it. This decorator instructs MindSpore to compile the function into a static graph when the code is executed. Additionally, the setContext API offers a JIT syntax level parameter, which allows you to specify the level of syntax support for static graphs. You can choose strict for basic syntax with optimal performance or lax for more complex syntax with higher compatibility depending on your specific needs. Here is an example.
Let me see. So this construct function is decorated with JIT and the PyNative mod is used. But you didn't specify the syntax level.
Yes, lax is used by default if the syntax level is not specified.
Alright, I think I understand how to work with static and dynamic graphs in MindSpore now. But what happens if I unintentionally use unsupported syntax in my static graph code? Or if I'm unsure whether certain syntax in a function is fully supported in static graph mode?
No need for fret. MindSpore has you covered. It employs a JIT fallback mechanism to ensure support for as many syntaxes as possible within the static graph mode. During graph compilation, MindSpore first parses your Python code. The JIT fallback feature comes into play here, identifying any unsupported syntaxes, such as methods involving third-party libraries, object creation via class names, and unsupported Python native functions. When these unsupported syntaxes are detected, they automatically fall back to the Python interpreter for interpreted execution.
Fantastic! This way, I can harness the performance advantages of static graphs and the flexibility of dynamic graphs simultaneously.
So we've covered a couple of key design concepts on MindSpore, the functional and the OOP fusion programming paradigm, and the combination of dynamic and static graphs. What else do you want to know about MindSpore?
I'm concerned about distributed training. With the rapid advancement in deep learning, the size of datasets and the model parameters has grown exponentially to enhance neural network accuracy and generalization. Distributed training has emerged as a critical trend to address the performance bottlenecks of ultra-large scale networks. However, in traditional manual parallelism, users must write code involving communication primitives to manually partition a model across multiple nodes for parallel training. This demands a deep understanding of concepts like graph slicing, operator slicing, and cluster topology, which can be quite challenging for newcomers. How does MindSpore assist users in overcoming these complexities in distributed training?
MindSpore offers robust support for various distributed and parallel training modes. For instance, in data parallelism mode, you can utilize the MindSpore dataset module, which provides parameters like num shards and shard ID for effectively partitioning training datasets. Furthermore, you can write network code for distribution in the same manner as you would for a standalone network. This is made possible because even though each device executes models independently during forward and backward propagation, the network structure remains consistent. The key is to ensure that the initial values of network parameters are consistent across devices to maintain synchronization.
You mentioned the synchronization, which is indeed crucial in distributed training. Could you elaborate on the synchronization method that MindSpore employs? Specifically, does MindSpore support both synchronous and asynchronous training?
MindSpore primarily employs a synchronous training method, which ensures that all processing units are synchronized in terms of model updates. Before each training iteration, the parameters on all devices are synchronized. While asynchronous training might offer faster training, it comes with potential risks in terms of model convergence and consistency. Therefore, MindSpore places a strong emphasis on synchronous training for stability and reliability.
Yes, reliability is paramount for the accuracy of distributed training. If I'm not mistaken, MindSpore also provides automatic parallelism, right?
Absolutely. MindSpore offers both semi-automatic and automatic parallel modes. The automatic parallel mode combines data parallelism and operator model parallelism. In this mode, MindSpore automatically constructs cost models and identifies parallel strategies that lead to shorter training times, selecting the most appropriate approach.
Could you explain how MindSpore determines the optimal parallel strategies?
MindSpore employs automatic search for operator parallel strategies, utilizing 3 different search algorithms: dynamic programming, recursive programming, and sharding propagation.
What exactly do these algorithms do?
Dynamic programming aims to find the optimal strategy based on the cost model, but can be slow for large network models.
What kind of cost model is used?
The cost model is built around training time, considering memory-based computational overhead and communication overhead on the Ascent 910 processor. Next is recursive programming, which rapidly generates optimal strategies for large networks or extensive multi-card slicing. Its cost model based on symbolic operations offers flexibility for various accelerator clusters. Lastly, there is sharding propagation.
Judging by its name, I assume this algorithm propagates parallel strategies from operators with configured strategies to those without.
Exactly. When strategies are propagated, the algorithm strives to choose strategies that result in minimal tensor redistribution costs.
How does the semi-automatic parallel mode differ from the automatic one?
In the semi-automatic mode, users are required to manually configure the sharding strategy while the rest of the process remains the same.
Thank you for the clarification. This gives me a good understanding of how MindSpore handles automatic and semi-automatic parallelism. Shifting gears a bit, I'm also quite interested in the operators within MindSpore. From what I understand, mainstream AI frameworks often define operators to be intuitive and user-friendly, making them easily understandable and accessible. Each operator is designed to handle a specific computing workload, varying in computational complexity. However, these user-centric approach to operator definition doesn't necessarily lead to high efficiency or the optimal utilization of hardware resources. Does MindSpore tackle this issue differently?
Absolutely, MindSpore approaches this challenge with a unique design philosophy. But before we delve into that, let me ask, what are your insights into the disadvantages of operators in other mainstream frameworks?
Well, there are a couple of key issues. First, complex and computationally intensive operators can be challenging to slice and optimize for high performance, leading to suboptimal hardware utilization.
This is a valid concern, especially with complex operators.
On the flip side, simple operators execute so quickly that devices often end up waiting for data input and output, introducing latency and consequently reducing hardware utilization. Additionally, in devices with multi-core or many-core architectures, factors like small operatorships or other reasons can result in low degrees of parallelism, leading to idle cores and further decreasing hardware utilization.
You've highlighted a critical challenge, particularly in domain-specific architectures. Maximizing hardware operator performance while maintaining ease of use has been a significant hurdle. In contrast to the conventional approach of separating the graph and operator layers, MindSpore adopts a graph kernel fusion technique for collaborative optimization. This technique has shown significant benefits in training speed, especially in typical networks used for tasks like natural language processing and recommendation. The main reason is that these networks often comprise numerous small operators, creating ample opportunities for fusion optimization.
That's fascinating. It seems like MindSpore's approach to operator optimization can truly enhance hardware utilization and efficiency in AI tasks. I'm particularly intrigued by the mention of the graph kernel fusion feature. Could you provide more in-depth information about these specific aspects? I'm eager to delve deeper into how it contributes to MindSpore's overall optimization strategy and its implications for AI deployment.
Absolutely. In the graph layer, the primary concept is to break down composite operators, enabling cross-operator aggregation and optimization. The next step involves partitioning the kernels, essentially the kernels themselves. The result is an optimized computational graph that's subsequently passed to MindSpore AKG as subgraphs for further backend optimization and code generation. This approach brings about performance improvements in two critical aspects: enhanced cross-operator performance optimization and fusion operators at the optimal granularity.
MindSpore AKG, what exactly is that?
AKG stands for Auto Kernel Generator, and it's a core component of MindSpore.
The name Auto Kernel Generator seems quite indicative of its purpose. Shifting gears, I'd like to discuss the security and trustworthiness of MindSpore. AI as a general technology brings great opportunities and benefits, but also faces new challenges in security and privacy protection. Now, I'd like to inquire about your understanding of the common security and privacy problems in AI application scenarios.
Certainly, one significant issue is the unintentional collection of sensitive and private data during the training process. If such data is learned by a model, it could pose privacy risks when the model is used. Additionally, there's the concern of model assets being susceptible to theft and models becoming obsolete due to data drift.
You hit the nail on the head. Another pressing problem is the vulnerability of AI models to adversarial attacks. So, how does MindSpore tackle these challenges and risks?
This leads us to MindSpore Armor, which is MindSpore's security tool. Let's delve into the overall design of MindSpore Armor. What specific aspects are you interested in learning more about?
I'm particularly interested in two aspects of security: model robustness and model asset security. The concept of privacy leakage risk assessment also piques my interest.
Alright, model robustness involves ensuring that AI models can withstand both natural and adversarial perturbations. MindSpore Armor provides a comprehensive set of features, such as generating natural perturbation examples, creating black box and white box adversarial perturbations, detecting adversarial examples, conducting adversarial training, and utilizing AI further for fast testing. These resources empower users to swiftly and effectively assess the resilience of AI models and enhance their attack resistance capabilities.
Excellent! Now, regarding model asset security, how does MindSpore safeguard the key assets of models during transmission, deployment, and runtime to prevent theft?
The structure and weights of AI models are the key assets. MindSpore Armor addresses this concern by offering model file protection through encryption and lightweight model safeguarding while structural parameter obfuscation. In federated learning scenarios, it also ensures secure multi-party computation with lossless precision to thwart attempts at model theft.
That sounds like a robust set of features for assessing model robustness and safeguarding model assets. Could you also shed some light on privacy leakage risk assessment and how MindSpore Armor addresses this specific concern?
Privacy leakage assessment involves utilizing technologies rooted in membership inference attacks and reverse engineering attacks to evaluate the vulnerabilities associated with potential model privacy leakage.
Thanks for that explanation. Now, since we just discussed MindSpore security tool, could you tell me about any other tools that MindSpore provides?
Certainly, in the overall MindSpore architecture apart from MindSpore Armor, another important tool is MindSpore Insight. We can properly guess its purpose based on the function it offers.
Let me think. Network debugging, performance tuning, accuracy tuning. It seems like a debugging and optimization tool.
You are on the right track. MindSpore Insights is indeed designed for visualized debugging and optimization to help users achieve better accuracy and performance. MindSpore Insight offers functions that cover training process visualization, training lineage, scalar comparison, performance profiling, and accuracy debugging.
Among these functions, I'm particularly interested in training lineage and scalars comparison. Could you provide more details on those?
Absolutely. The model lineage, dataset lineage, and scalars comparison dashboards are important components of MindSpore Insights. Model lineage displays the parameter information of all training models. For example, in the model lineage function area, the model parameter information is visualized. You can select a specific area in the columns to display the model information within that area. And in the model list, you can sort the model information by specified columns. In the overview area, information about optimization objectives and related parameters is displayed. You can select an optimization objective to view the importance of parameters, and then click the histogram to view the scatter plot of parameters and the optimization objective.
Thank you for the demonstration, Harry. Model lineage seems like a powerful tool for tracking model parameters and understanding their importance in optimization. Could you also provide more details about dataset lineage and how it complements the model lineage function in MindSpore Insight?
Certainly, data lineage shows data processing and argumentation information for all training runs. You can select a dataset to view its related parameters, similar to how model lineage works. Just like before, you can select a specific area in the columns to display the parameter details.
Data lineage appears to be a valuable addition to MindSpore Insight too, for understanding how data processing and augmentation impact model training. It's impressive how these tools work together to provide a comprehensive view of both model and the data aspects. I can see how they can greatly assist in optimizing machine learning workflows. To my understanding, MindSpore Armor and the Insight help with model training. Does MindSpore also provide tools for model deployment?
Absolutely. If you ever plan to deploy a model as an online inference service in a production environment, you should consider using MindSpore Serving.
Well, I don't have immediate plans for production deployment, but I'm curious to know what this tool offers.
That's a good attitude. Even if you don't need it right now, it's beneficial to learn about it in advance. Once you've trained your model using MindSpore Serving enables you to create an inference service based on that model.
Could you explain how MindSpore Serving actually works?
Certainly, MindSpore Serving simplifies model deployment and execution by offering various functions such as customizable data pre-processing and post-processing, distributed inference, gRPC and RESTful client APIs, and batching, which divides and combines requests to match the model's batch size.
It seems like deploying a service with MindSpore Serving is straightforward. Can you provide an example to illustrate how a model is deployed as a service?
Certainly, let's use the ResNet 50 model as an example. Assuming you've already installed MindSpore and MindSpore Serving as I suggested.
Okay, I've got MindSpore and MindSpore Serving installed.
Right now, let me introduce the concept of a servable in MindSpore Serving. A servable is an object deployed on a worker node to provide inference services. It can consist of one or more models and offer different services based on a single model.
So I can use one model for multiple tasks.
Exactly. It depends on the data pre-processing and post-processing. For instance, ResNet 50 can be used for classification. What specific classification task would you like the service to perform?
Give me a moment to think about it. I'd like the service to take an image as input and output the most likely animal in the picture, as well as the top 5 most likely animals and their probabilities.
Okay, so you have two subtasks with the same pre-processing but different post-processing.
That's right. One is for the top category name and the other is for the top 5 categories and their scores.
Then we can represent this service using a flowchart like this. Each subtask is handled by a separate method within the same servable. Now we will specify the name, input, output, stages, and data flows of each method.
What do you mean by stages?
A stage can be a Python function or a model. In your case, each method has 3 stages.
Got it.
For this task, we will prepare the files like this. The root folder name ResNet 50 serves as the servable name. Folder 1 contains the model file, and servable config is the servable configuration file.
So I define the processing steps in the configuration file, right?
Exactly, and more specifically, you will define the stages, as I mentioned earlier.
Alright, let me start by importing the necessary packages and defining the possible layouts. Then, convert the image into a tensor that can be recognized by ResNet. The image data needs to be decoded, resized, and normalized, and the channels need to be computed.
Perfect. You've got the data pre-processing steps right. Now let's move on to the post-processing functions. First, I will define the one for outputting the most likely animal.
Great, that makes sense. Now for the second post-processing function that gives the top 5 categories and their probabilities.
With the first and third stages defined for both methods, we are now ready to tackle the second stage, which is the ResNet model. We can declare the model like this.
Since all 3 stages are now defined, I assume our next step is to incorporate these stages into our methods.
Precisely. Defining the methods is straightforward. We'll simply add the stages to the methods and establish the data flow by specifying the inputs and outputs of each stage. That's all the code for the server.
It seems like we still need to deploy a client to interact with the server, right?
Indeed, Sophia. The client code is also quite straightforward. Here's an example of a gRPC-based client.
I see. The client's main tasks are sending data to the server and displaying the return data from the classified top 5 method.
Precisely. You've now gained a good understanding of MindSpore architecture and some essential tools it provides. You're well prepared to try your hand at training and deploying your own models.
Thanks, Harry. I'm looking forward to putting this knowledge into practice. If I run into any issues or have further questions, can I reach out to you for help?
Absolutely, Sophia. Feel free to reach out anytime you have questions or run into any issues. I'm here to help, and I'll do my best to assist you in your journey with MindSpore. Good luck with your model training and deployment, and don't hesitate to ask me or submit issues for guidance in the MindSpore community whenever you need it.
I appreciate that.
In addition to its efficient framework and user-friendly tools, MindSpore goes above and beyond by offering a wide array of suites and extension packages tailored to meet the diverse demands of the AI community and the scientific computing enthusiasts. This encompasses a broad spectrum of fields, including but not limited to computer vision, natural language processing, electromagnetic simulation, and molecular simulation.
These invaluable resources can empower researchers, developers, and scientists to harness the full potential of AI across various domains. We'll delve deeper into these specialized packages in the upcoming session of MindSpore TechDay, so make sure to stay tuned for a comprehensive exploration of their capabilities and applications.
See you next time.
Bye!